Hi, and welcome to Material Physics Lesson 3. Today we're going to be looking at angular momentum. Now this isn't specifically something to do with material physics per se, but actually underpins a lot of the quantum mechanics on which the material physics is then overlaid. So in other words, in order to understand the movement of the tiny particles, you need to understand angular momentum, and then in doing so you can understand them, and then you can understand why the metal is bending, because it's dependent on the properties of the very small particles within it. It's also just an incredibly useful thing to know before you go to university. It's probably the simplest thing we don't do on A-level physics. So it's a really good idea to just wrap your head around. So what I'm going to be doing today is taking you through what angular momentum is and how it differs from normal momentum. So these are things about momentum that you should already know. What we're going to be doing is looking at the angular version, and through that explaining what angular momentum is. So, what is angular momentum? At a very basic level, it's a measure of how much something is spinning, which wouldn't be that interesting except for one really neat thing, which is just like normal momentum, angular momentum is conserved. So how much something is spinning is conserved. The classic example of this is a figure skater. If a figure skater is spinning with her arms out wide and then draws them in, she'll start to spin faster. That's because of angular momentum. Her arms are carrying some angular momentum. They are spinning. When they are brought into her body, all the angular momentum that was in her arms is transferred to her body, and therefore her body speeds up because angular momentum is conserved. It has to go somewhere, so it's transferred from the arms to the body. So that's basically what angular momentum is. It's a measure of how much something is spinning. So momentum is defined as mass times velocity. The actual definition of angular momentum is a real faff, so we'll get to that in a sec. Don't worry about that too now. However, the equation that is useful is angular momentum L is equal to I times omega. So angular momentum L is equal to I moment of inertia times omega, which is just radial velocity, or angular velocity, which we already know, we've studied that. So we've got two new ideas, L, angular momentum, I, moment of inertia. So what do each of these mean? Well, L is just angular, is, as we said, angular momentum. I is basically the equivalent of mass. So rather than being mass times velocity, it's moment of inertia multiplied by radial speed. So this is your velocity component, this is your mass component. I is basically a measure of how difficult something is to turn. It's defined actually out of this equation. So I is defined this way. It's defined as L divided by omega. So how much angular momentum something would have at a given speed. So it's just defined out of that equation. But we can also define our moment of inertia another way, and that's through this. So we know that force is equal to the rate of change of momentum divided by rate of change of time. So that's just something we already know about momentum. The faster your momentum is changing, the greater force there must be on it. Well, there's a turny version as well, you might already have heard the name of, and that's torque, which is given the symbol tau. Just a little tiny t from the Greek alphabet. And that's our rate of change angular momentum with time. Okay? But if you think about it, just in the same way that a more massive object would require a greater force to push, something with a bigger moment of inertia, which remember is just how much it resists being turned, will create a bigger torque to turn. So you can define moment of inertia that way as well. Something with a big moment of inertia is going to need a load of torque. Something with a small moment of inertia is only going to need a small amount of torque to get to the same spinning speed. So therefore, moment of inertia is just how much it resists being turned. Angular momentum is how much of that moment of inertia it has multiplied by how much it's turning. So if you've got something really heavy, really difficult to turn, and it's going really fast, it will have loads and loads of angular momentum. Yeah, and instead of it all being about forces moving things, it's all about torques moving things, our turning forces. So rather than having force, we have torque, and rather than having mass, we have the moment of inertia. So that's our parallel for torque, and that's our parallel for mass. Okay, moving on. There's only really one type of momentum, in the classical sense. It's just things bashing into each other and going in a straight line. Angular momentum, maddeningly, has two different types. And they are called the spin and the orbital. Spin angular momentum is the simpler one. That's just something turning, but the centre of mass is staying in the same place. So if you think about somebody just spinning on the top, like a figure skater, what have you, that is called just your spin angular momentum. But there's another type of angular momentum as well, and that's when the centre of mass itself is also orbiting something. So if I was to go like this, my centre of mass was to orbit a point here because I was spinning around like that. If you imagine a gyroscope on its side, spinning round and round and round, the centre of mass isn't in the same place. So now it's got what we call orbital angular momentum, and it's also spinning, so it's got spin angular momentum as well. So it's got two different types, spin and orbital. Interestingly, if you think about it, you've got to define an axis for the centre of mass to be moving around. So orbital angular momentum is dependent on which frame of reference you choose. However, what you'll find is that the total angular momentum, which is the spin and orbital added together, will be conserved regardless of reference frame. So, total angular momentum is equal to the two different types. Spin, which is moving around the centre of mass, and orbital, which is when the centre of mass is moving around. So there you go, there are two different types and you have to sum them, and it's the vector sum as well, exact same as momentum, so just be careful about that. It's not just monodirectional. The vector sum of all the spin and all the orbital angular momentums give you the total angular momentum. Alright, almost there, just two more ideas and then you'll have an overview of what angular momentum is. Right, Newton's third law tells us that for every action there must be an equal and opposite reaction. For every push there's an equal push in the opposite direction, yada yada. Interestingly, the same thing happens with torque. Every time you turn something, you have to exert an opposite turning force against something else. So if I crank a wheel one way, it'll exert an equal and opposite turning force on me. So all the torques also cancel each other out. So exactly the same way that within a closed system there's overall no force, because equal and opposite forces. Same thing, in a closed system there'll be no overall torque, because all the turning forces will cancel each other out. So therefore we can put in closed system no overall torque. So if you do the vector sum of all the torques, you'll get 0. Finally, classical momentum is linear. It's in a straight line. And if there's more than one force acting on something, then they'll all just cancel out, and whatever force you're left over with, it'll just move in that direction. Things don't move in more than one direction at once. However, spinning stuff is a nightmare. So, our moment of inertia, I, okay, there can be two different ways of defining it. You know I said right at the beginning, I is a faff? Now I'll show you why. So, our moment of inertia, if something is constrained within one plane, so it can only spin in one plane, then the moment of inertia is just the square of all the masses from the distance to the centre that it's spinning around, and it's simply just a number. So if you just get a flywheel, you lock it in place, you spin it around, it's just a number, it's just a scalar. So if it's constrained to one plane, then I is just scalar. However, if something can spin however it wants, and can spin in all three dimensions, then our moment of inertia, will actually be defined as a 3x3 matrix. So there you go. Isn't that fun? So you could say this nonsense here is the moment of inertia of this big spinny thing. And yeah, so that just depends whether you've locked it into one plane for this one, or whether it can rotate in all three dimensions. So there you go. Angular momentum. We'll be continuing this on later in a week. There's a question underneath. I hope you're enjoying yourself.